homogeneous solid cylinder of mass 1 kilogram and radius 10 centimeters moves in a gravitational field similar to that of Earth, 9.81 meters per second squared, up an inclined plane. Its initial velocity is 5 meters per second. Friction can be neglected. Okay, so the cylinder is rolling. What is the maximum height h? So the cylinder slides. What is the maximum height it reaches? Okay, so for rolling, actually for both of these, they're going to be a conservation of energy. So what we're going to start with is energy kinetic initial plus energy potential initial equals energy kinetic final plus energy potential final. We're going to say this is the ground, h equals 0, and it's going to be h final up here. And the potential energy is based on position. We're going to assume that its initial potential energy, in this case, is going to be mgh. And so the initial potential energy is going to be 0. And when it comes to a stop at the top, if it's maximum peak, its kinetic energy is going to be 0 because kinetic energy is based on motion. And so, yes, and then energy kinetic. It's energy kinetic, since it's initially rolling, it's going to have kinetic energy based on its linear motion and also its rotational motion. So I'm going to write that as energy kinetic linear. It's going to be 1/2 mv squared, and its rotational energy is going to be 1/2 I omega squared, where I is the moment of inertia, and omega is the angular speed. And then that's going to equal its final potential energy, which we're just going to call mgh. So the first question then is, all right, so what is I and omega? So one assumption I made here, which I didn't explicitly mention, is they say friction can be neglected. I'm going to say friction can be neglected in terms of losing energy. It has to have friction, otherwise it can't roll. The whole idea of rolling is that it rolls without slipping. Without slipping means that there's friction, but we can assume there's no energy lost due to friction. All right, so now what we want to find out here is this I. Moment of inertia is based on the geometry of the object that's spinning or rotating, and a cylinder is going to be similar to a disk, just with more length to it, more height. And so the moment of inertia of a disk, this is just something I happen to know. You can look it up. It's one of those things you're assumed to be able to look up or assumed to know. It's 1/2 mr squared. And then, since we assumed that it's rolling without slipping, we know the relationship x equals r theta, v equals r omega, a equals r alpha. And this is actually a cross product, but we're not going to go into that sort of nuance here. X equals r theta. And the way I remember this is I just do the first one first. So if you have a circle, the distance around a circle is its circumference, 2 pi r. And if you look at angular terms, the angle around a circle is 2 pi. Radius is r. And it's like, oh, okay, so the left side equals the right side. And then it follows the same pattern down with speed and acceleration. So what we're going to use, though, is this relationship here, which will then give us omega equals v over r, or more specifically, omega squared equals v squared over r squared. So putting this all together over here, we get 1/2 mv squared, still 1/2 mv squared, plus 1/2 I, which is 1/2 mr squared for a cylinder, and then omega squared, which we said was v squared over r squared. V squared over r squared, and that's going to equal mgh. I think we're told the mass of the object. Doesn't matter, we don't care. Because if you look at this, all the masses cancel out. Conveniently, the r's, r squared, also cancels out. And we are left with, can I use this color? Maybe. 1/2 v squared plus 1/4 v squared equals gh. 1/2 plus 1/4 is 3/4 v squared equals gh. Rearranging this, h then is 3v squared over 4g, which in this case is going to be 3 times, I think it's 0.5. No, 5. 5 meters per second squared. Or 5 meters per second. I should make sure I read that correctly. Yep, 5 meters per second. 5 squared over 4 times 9.81. This is going to be, I'm going to put this into a calculator. And this is going to be 3 times 5 squared all over 4 times 9.81. That gives us about 1.91 meters. All right, so now the question is going to be, assume the cylinder slides, not, so this time friction is neglected. There is 0 friction because it's sliding up. What is the maximum height it now reaches? So I'm going to copy and paste this conservation of energy, not really because it saves us time, because I want to show that, hey, exact same concept here. So this is now going to be part B. The potential energy is still 0. Initial potential energy is still 0. Final kinetic energy is still 0. But now our kinetic energy is solely going to be 1/2 mv squared. Since it is sliding, no longer rolling, we could write 1/2 I omega squared as well if we wanted. But since it is sliding, i.e. not rolling, that would imply that omega is 0. Therefore, that whole side is 0. So then we've got mgh. Following through on these calculations, masses go away. We get v squared over 2 equals gh. Therefore, height, which is going to be its maximum height, is v squared over 2g, which is going to be 5 squared over 2 times 9.81, which is going to calculator. We have 5 squared over 2 times 9.81, and it gives us a much smaller number of 1.27 meters. So to backtrack what we did here, this is conservation of energy. Conservation of energy meaning that we don't have any energy lost. We can take into account all of our energy. In our accounting practice, we don't have any energy that gets misplaced. So since no energy is misplaced, we know that all the energy that we start with is going to be all the energy that we end with, which means conservation of energy. So we said energy kinetic plus energy potential initial equal to energy kinetic plus energy potential final. We said initial potential energy was 0, final kinetic energy was 0 because it came to a stop, and kinetic energy is based on motion. We then assumed it was rolling without slipping, meaning that this relationship is true. And with that relationship and the known moments of inertia for various shapes, in this case a cylinder, we're able to basically convert moment of inertia I and omega into their linear equivalents, their linear analogs, and solve the equation. And what we found was it went higher when it was rolling than sliding. And the reason for that is because when it's rolling, it has energy from both its forward linear motion and its spinning, where when it's sliding, it only gets the energy from its linear motion. Therefore, it's going to be able to reach higher. When it converts its energy to potential energy, it's going to have more potential energy when it had sliding and rolling, as opposed to when it only was sliding, which seems reasonable. So hope that helped. See you next time.